Okay, so someone's asking about number 27. Um, so for number 27, um, it's asking how many of the first 2019 positive integers have no single digit prime factors. So those are 3, 7, oh, missed 5, sorry, 5, and 7. Those are the only 3. So, every like if you multiply these few numbers, say you get like n, every amount of numbers, there's going to be a fixed number of integers that are not divisible by these 3 numbers. Every third number is divisible by 3, so we can say, well, first let's multiply these. So if you multiply them, you get 105, I believe. And 1/3 of these numbers will not be 2/3 of these numbers will not be divisible by 3. 4/5 of these numbers will not be divisible by 5, and 6/7 of those numbers will not be divisible by 7. Or actually, yeah, so. Actually, we should use complementary counting here, so 1/3 of them are divisible by 3. A fifth of them are divisible by 5. And a seventh of them are divisible by 7. Now here we actually overcounted because some of these numbers are counted twice. For example, 15 is divisible by 3 and 5. However, we counted it both here and here. So we actually want to subtract all the numbers that are divisible by a combination of any of these 3 numbers. So a 15th of these numbers are divisible by 3 and 5. Um, 1/21 are divisible by 3 and 7. And 1/35 are divisible by 5 and 7. However, we actually overcounted again here because we actually didn't consider that the fact that all 3 of them can be divisible. All 3 of them divide into here. So here we counted that we counted 105 3 times. Here we also counted 105 these 3 times, so we need to add it back again. So this is the total amount of numbers that do not fit this condition. So we need to do 1 minus that. And let me just calculate this really quick. We should get that there's 57 of these numbers in total, so you need to subtract that from the total 105. So then you get that every 105 numbers, there are 48 numbers that do fit this condition. Okay, let me just get rid of some of this. Hold on. Okay. So 2019. Oops. 2019 has can fit 19 105s in it. And the remainder should be 24. So there's 24 numbers that do not do not fit into this pattern of 105. So we can actually just write all of them out. It shouldn't take too long. So the first number that is not in this pattern is 1996. So this number isn't wait, hold on. This number is good, so we can include that. And then 1997 also fits our pattern, so we can include that. 1998 we cannot include, so I'll just skip that, because 1998 is divisible by 3. 1999 is good. 2000 we cannot, because it's divisible by 5. 2000, so I'll just keep a tally here. 2001 we can also not include, because it's divisible by 3. 2002 is divisible by 7, so we can't keep that. 2003 is not divisible by any of these numbers, so you can have that. 2004 is divisible by 3, so we do not include that. 2005 divisible by 5, so no. 2006, yes, we can keep that. 2007 is fine. No, sorry. 2007 is divisible by 3, so we cannot include that. 2008 should be fine. 2009 is divisible by 7. 2010 divisible by 5. 2011 is fine. 2012 is also fine. 2013, I think we were on. Yeah, 2013 is divisible by 3. 2014 is fine. 2015 divisible by 5. 2016 divisible by 7. 2017 is not divisible by any of these. And 2018 is also not divisible by any of these. And 2019 is divisible by 3. So in total, from this 1996 where this pattern ended, we have 11 numbers. So remember we said that the pattern of 105 repeated 19 times, and we said in each of them there was 48 that did fit this condition. So we do 48 times 19, and then plus the 11, and you should get 923. Okay. Hold on. if you have any questions about that, feel free to ask me. Okay, so it seems nobody has questions about this. Is it fine if I erase this now? Okay. Well, since no one's asking any questions, I'm just going to go over some problems that I think are pretty interesting. So this number 25, it's asking it's asking for, so basically you have an equilateral triangle with side length 11, and then there's a bunch of like these points inside of that triangle, just like this. And it's asking, if you randomly select the points, what's the probability that you're going to have that there exists a triangle where the distance from this point P to each of the sides is its side lengths. So the way to do this problem, sorry, can't, okay. So a little known, this fact might be a bit obscure, but it's actually a fact that if you take any point in the triangle, the sum of its length, the lengths from that point to the side lengths, is actually that's always going to be the same length, and it's always going to be equal to the altitude of that triangle. So basically, now that we know that, and also so based on the the triangle side lengths like thing, where a side A cannot be greater than the other side, the sum of the other sides. Oh, sorry, C. We can, because we know that A plus B plus C always has to be equal to the altitude, we can figure out like how this, like where this can occur. So basically, the height of this triangle, this is 11, so this 30, 60, 90 ratio, so this is going to be 11 over 2, and this is going to be 11 square root 3 over 2. And then you can basically change BC into 11 square root 3 over 2 minus A has to be greater than A. And remember that A, in this equation, A has to be the greatest side. So that's just something to keep in mind for later when we put this back into the diagram. So from this we get that A has to be less than 11 root 3 over 4. Okay. So if you notice, this value is actually just halfway up the triangle. And so anywhere inside of this halfway thing will work, because all three sides will be less than 11 root 3. But if you go past this line where the greatest side is going to be 11 root 3, 11 root 3 over 4, then like say here, say this length is like 10, then that's not going to work anymore, because the greatest length is not less than this value, which we showed that it had to be before. So all of these points inside this middle triangle, there is, you can just count 1, 2, 3, there's 10 points here. And 1, 2, each side has 12 points, or the greatest side has 12 points. Each side has one less, so it's just an arithmetic series. 12 times 13 over 2. Sorry if that's a bit messy. Which is going to be 6, 60, 78. Or, yeah. So the probability is going to be 10 over 78. Which is equal to 5 over 39. Okay. Okay. The next interesting problem is going to be number 28. So this problem, you're obvious. It's maybe feasible to calculate out this, but finding the square root of that number is going to be pretty difficult. So basically, what we're going to do is we're just going to estimate. So notice how 1/9 is approximately equal to 0.11111, etc. So we can estimate this value as 1/9 times 10 to the power of 1, 2, 3, 4, 5, 6, 7 to the power of 8, I believe. Let me just see. Sorry, to the power of 9. And then this value is going to be approximately 10 to the power of 8. And then plus 4. Now this value is going to be very small compared to this, so we can kind of just ignore it. And then so from these two we get 1. So this value is going to be approximately 1/9 times 10 to the power of 17. So square root that, you get approximately a third times, hold on, let me just check this. Okay, a third times 10 to the power of 8, and then square root 10 and then, hold on, I'm having, me see. I'm pretty sure I did something wrong here. Oh, yeah, sorry. This should actually be right here. This should actually be to the power of 8, not 9. So then this is 16. And you just get rid of that. So then here, this is going to be about 3, 3, and then there's going to be 6 more 3s. So that's approximately the value, but we need to be a little bit more specific. So from these, like the units digit of this number and this number, so that means the units digit of this multiplied together is 1 plus 4, so the units digit of this whole thing is 5. And the only thing that, like, if you square root a number that has a units digit of 5, the unit digit is going to be 5. So then we can approximate that it's going to be 3, 3, 3, 3, 3, 3, 3, 5. So that's approximately going to be the value of this. If you have any questions about that, you can just put it in the chat. Okay, so it seems this is all good, so let's move on to the next one. This last problem is pretty interesting, so I'll go for that one. The problem is Hank is building an increasing sequence of integers. The first term is 1, the second term is 2. So the requirement for this sequence is that no 3 numbers can form an arithmetic sequence, and so these are the first 5 numbers. So the first thing we want to do is extend this list and see what sort of pattern we can find from it. The next number here is going to be 11, 13, and then it should be 14, and 28. So there's something interesting we can realize here. Here you can see there's a doubling. You can see there's a doubling. And then, so what we kind of notice about these numbers is that if you put them, these, like, they're always 1 plus the power of 3. Here, it's 3 squared plus 1. This one is 3 cubed plus 1. So something we might want to do is, and also 4 is 3 plus 1. So something we might want to do is write this list into base 3. And then, so 1 will still be 1. And then it'd still be 2. 4 is going to be 11. 5 is going to be 12. 10 is going to be, what is 10? 10 should be 101. 11 is 11-1. Then you're going to have 11-2. Oh, sorry. There's also going to be... Here, I'll just change that. We're going to have 112. And then you're going to have this number. So what we kind of noticed about this is that the singles, the units digit is always going to be 1 and 2, 1 or 2, and the every other digit will either be 1 or 0. So 777, if we write that into base 3, 777 just happens to be 3 to the power of 7, I believe. So that's going to be 2, 3, 4, 2, 1. Okay, so that's going to be 729 to the power of, in base 3. So every single number that has either 1 or 2 as the units digit and 0 or 1 as the other as the every other digit is going to work. So basically what we can do is 1, 2, 3, 4, 5, 6. So there's going to be 2 options for these 6 digits. It's either going to be 0 or 1. And there's going to be there's going to be 2 options for the units digit. So in total there's going to be 2 to the 7, which is 128. Okay, if you have any questions about that, you can ask them in chat. Okay, so then that's just gonna be it for tonight, and I'll see you next time. Bye.